Good morning, good afternoon, and welcome to the Optica Industry tutorial. Thank you for joining us for the fiber-based femtosecond lasers, robust, reliable, and ready to use. My name is Elena Diez, and I am the Director of Laser and Medical Technologies at Optica. Optica brings together the global optics and photonics community across research, industry, and applications. Through our industry tutorials, we aim to connect technical expertise with practical deployment, helping researchers, engineers, and companies understand how optical technologies are moving into real systems. Today's tutorial focuses on a very important shift in the ultrafast lasers. Femtosecond lasers are essential for many high-value applications, including multiphoton microscopy, 3D nanoprinting, terahertz spectroscopy, optical frequency comms, and photonics quantum technologies. But the challenge is no longer only generating very short pulses. The challenge is delivering those pulses in a compact, stable, low noise, and reliable platform that can be used routinely and integrated into instruments. That is where fiber-based femtosecond laser architectures become highly relevant. Today, Menlo Systems, a corporate member, will present its approach to fiber-based femtosecond laser technology, with particular focus on its Figure 9 mode locking architecture. At high level, Figure 9 is Menlo Systems' proprietary fiber laser cavity design. It's based in a non-linear amplifier loop mirror, or NALM, and uses all polarizations maintaining fiber architecture to support robust, self-starting femtosecond fault generation. For the users, this is the important point. It's very practical. How does the laser's architecture translate into stable operations, low noise, reduced alignment sensitivity, easier synchronization, and lower cost of ownership? That is the focus of today's discussion. Menlo Systems is a recognized provider of high-precision photonics instrumentation, including femtosecond lasers, optical frequency comms, and terahertz systems. The company has built a strong position in applications when laser stability, timing precision, and long-term reliability are critical. Today's tutorial will connect the underlying laser architecture with real application requirements, from microscopy and nanoprinting to terahertz spectroscopy and quantum photonics. Let's start to introducing our two speakers from Menlo Systems for today. First, Dr. Jaroslav Sperling. Jaroslav is business developer at Menlo Systems. He joined the company in 2021, bringing experience for sales-related roles across the photonics industry. His technical background in his ultrafast laser spectroscopy is really exceptional. He holds a PhD in physical chemistry from the University of Vienna. Together with him is going to be joined Dr. Christian Mauser. Christian leads the product manager team at Menlo Systems. He joined Menlo in 2010 and brings deep technical expertise from the femtosecond laser R&D division. He holds a diploma from Karlsruhe Institute of Technology and a PhD from LMU Munich. Before we begin, let me tell you a few practical notes. Please submit your questions at the Q&A box during the presentation. You can also use the chat box. So just continue, let us know where are you coming from, what is your interest on this. And also, if you want to participate in the Q&A question and open your mic, please raise your hand when the moment is coming. All the Q&A will be at the end of the seminar. Okay, so for the moment, thank you to Jaroslav and Christian for clear and technical rich presentation. And please, the floor and the attention is all yours.
Thanks, Elena, for the introduction, and welcome everyone. My name is Jaroslav. I'm in business development for Menlo Systems. I'm happy to be joined by Christian Mauser here. He's the leading expert in our leading expert and product manager in femtosecond fiber lasers. Let me start with a brief introduction. Helena already she already introduced a lot. Still, I have a couple of slides I would like to share. a brief introduction to Menlo Systems and in particular how our story is connected to femtosecond fiber laser technology. So I think it's fair to say that Menlo Systems is widely known as having been the world's first commercial supplier of optical frequency comps. And for those of you who are not familiar with frequency comps, here is the schematics. Simply put, an optical frequency comp is a kind of special type of laser which generates a spectrum of equally spaced optical frequencies in frequency domain. And this resembles the teeth of a comp in frequency domain, and hence the name. 25 years ago, actually, we have an anniversary this year. Menlo Systems was co-founded by Ted Hench, the later Nobel Prize winner and pioneer of optical frequency comp technology. So this is our background, so to say. We will not go into many details or not go into details of frequency comps in this webinar, but let me briefly illustrate how they looked about 25 years ago. So occupying a whole, an entire laboratory, and how the technology advanced, how we have advanced this technology over the years, making frequency comps compact enough and robust enough to fit them into portable 19-inch rack systems. And really at the heart of these advances is Menlo Systems' proprietary fiber-based laser technology, which combines the scientific precision with industrial robustness. And yeah, it is this proprietary laser technology that we will take a closer look today. Let me conclude the introduction with a few key figures. So we are headquartered in Munich, Germany. We are well more than 200 people worldwide. We maintain subsidiaries in the United States, China, and Japan. Last but not least, we are embedded, so to say, in strategic partnerships with industry leaders such as Tor Labs and Hamamatsu. So this was the short introduction, and here come the topics of the day. So we will start with looking at what is at the heart of a femtosecond laser, the mode locking concept. We will introduce the figure 9 scheme. We will explore then the main building blocks of fiber-based laser systems and the principles or the art of modular design. Yeah, last but not least, we will highlight a couple of application examples from in both scientific and industrial settings. Okay, so let's now turn to what is at the heart of a femtosecond laser system. This is the mode locking scheme. So what is mode locking? Mode locking, simply put, is the process by which the cavity modes of a laser cavity self-organize, so to say, into a stable train of ultra-short laser pulses. And the common way to achieve this is by using so-called intrinsic saturable absorbers. What is this? So this is a device with intensity-dependent transmission. So a saturable absorber, it will absorb low-intensity light while high-intensity light is transmitted. And when there is a random intensity fluctuation in the cavity or a burst, it may pass through the absorber and mode locking can be initiated. Such a burst then circulates through the cavity and is getting amplified and compressed during each round trip until stable mode locked operation is established. Now, common implementation of a saturable absorber is a so-called semiconductor saturable absorber mirror, or CSAM. This is illustrated on the left here. This is essentially a mirror whose reflectivity depends on the light intensity. Low intensity light is absorbed, while high intensity light is reflected. CSAMs are, it's fair to say, I would say it's mature and well-established technology. They do have some limitations though, one of which is that their performance may degrade over time. And this has motivated the search for improved alternatives. So-called artificial saturable absorbers where no physical absorption takes place. So yeah, let's take a closer look at how they work. We start here considering a simple fiber splitter. So this is a device with 2 fiber inputs and 2 fiber outputs. And if light enters through one of the input fibers here on the bottom left, it is split equally between the 2 output ports. Now let's connect the 2 output ports and form a so-called fiber loop. What happens to the 2 portions of the pulse? They propagate in opposite directions around the loop and eventually interfere again at the splitter. And in the simplest case, this interference causes the entire pulse to be reflected back where it came from. In other words, the fiber loop behaves like a mirror. However, the situation changes if the 2 counter-propagating pulses from some reason acquire a relative phase shift before they recombine. And in that case, part of the input pulse may be transmitted into the second input port instead of being reflected. And now the key idea is if this transmission can be made dependent on the pulse intensity, effectively one may obtain an artificial saturable absorber. This principle has been employed in a so-called figure 8 laser. So it consists of 2 sections, a nonlinear amplifying loop mirror, this is the upper loop here, and the main resonator, the lower loop. The upper loop relies on an asymmetric arrangement of an amplifying doped fiber and a longer section of passive fiber. So if the intensity of a pulse entering from the lower loop is high enough, the nonlinear phase shift in the upper loop becomes large enough so that to allow transmission back into the main resonator where the pulse will propagate in clockwise direction. So as a result, stable pulses circulate in the lower loop here, while a fraction of the light can be coupled out as the laser output. For practical devices, the figure 8 scheme comes with a significant drawback. As it turns out, it can be difficult to achieve self-starting mode lock operation when using polarization maintaining fibers. However, one can build up on the loop mirror concept and advance it to the next level. This is the so-called figure 9 scheme. And I would like to draw your attention to a tiny thing here, which does a lot of magic. This is the phase shifter. It's called a non-reciprocal phase shifter. What does it do? Well, in essence, it allows to tweak the phase shift of the counter propagating pulses exactly the way you need it. And this allows to adjust the overall phase shift in such a way that at steady state, the loop mirror, it will operate in reflection mode rather than in transmission. So this in turn allows to straighten the lower resonator part into a linear arm. And at the same time, one can optimize this design for low intensities, so to achieve an easy self-start of mode locking operation. And I should also emphasize the flexibility of the linear resonator here. One can either couple the output directly into an output fiber, as is shown here, or one can employ a short free space section within the laser cavity. And this allows for straightforward integration of intracavity actuators that you might need, for example, for repetition rate tuning or CEP stabilization. Thanks to these features, figure 9 mode locking technology is I would call it not only the backbone of our femtosecond fiber laser portfolio, but is also the working horse of maybe not all, but most of our other products. Since figure 9 relies on an all polarization maintaining fiber design, it is efficiently decoupling the laser cavity from the outer world, if you wish. So like perturbations such as vibrations or temperature fluctuations. We have compiled a few data here. So for illustration, this is for example, power stability at shock testing up to almost 20 G, or temperature cycling over a range of more than 40 degrees C. So to wrap up, we look at technology that is robust. It guarantees self-start and mode-locked operation even in harsh environments. We look at a technology that is reliable. Even after many on-off, thousands of on-off cycles, it will provide the repeatability and excellent stability. And last not least, we look at a technology that we like to call ready to use. As we are looking at turnkey systems, there is no external cooling required, and they are truly maintenance free. So with this at hand, with the oscillator part, so to say, at hand, how can the femtosecond pulse trains generated by such an oscillator, how can we tailor them to meet specific application requirements? The answer essentially is a toolbox of modular extensions that we wanted to review here. So at the heart of the toolbox, of course, will be the oscillator. It will deliver the primary femtosecond pulse train. In time domain, this pulse train will have a certain repetition rate. Typically, it will be on the order of 100 megahertz. This can be customized to significantly lower or also higher values. In frequency domain, the pulse train will have a certain center frequency or center wavelength. For illustration, this shown here is a real-world optical spectrum of an erbium-based fiber laser, which is centered around 1560 nanometers. Not in all cases, but in most cases, I'd say the oscillator pulses will need some sort of amplification. Typically, average optical output powers up to 10 watts can be achieved. So just to give you some numbers, at 100 megahertz, this translates into pulse energies of up to 100 nanojoule. The pulse train typically will need some sort of dispersion management to ensure shortest possible pulses are delivered at the right point. So this is, for example, to compensate for the dispersion of an optical setup, so to have the shortest possible pulse really at the sample, or to pre-compensate the dispersion of a fiber beam delivery. As an example, for erbium-based systems, pulse durations well below 50 femtoseconds can be routinely achieved. In many applications, you might also want to modulate the pulse energies, or you might even want to pick individual pulses. As to fast modulation, this is usually characterized by rise fall time, so the time it takes to turn the power from fully off to fully on, or vice versa. And as illustrated here, we are typically looking at rise fall times on the order of 200 nanoseconds. Quite a few applications will require precise control of the repetition rate. So for example, you might want to stabilize the repetition rate, to lock it to some external reference, or to lock the repetition rate of one laser to another laser in a master-slave configuration. So this is also what is possible with the figure 9 scheme. Now let's turn to frequency domain to look at the tools for extending and tailoring the wavelength coverage. So for extending the wavelengths to higher frequencies or shorter wavelengths, of course, second harmonic generation or SHG is the working horse. What is shown here is the frequency doubled spectral output of an ytterbium-based system, frequency doubled to around 520 nanometers. I should also mention that you may apply SHG in series to extend the wavelength coverage even into the UV spectral range. To generate longer wavelengths, on the other hand, one way is to use some sort of frequency shifting that is particular to fiber lasers. This is the so-called solitone self-frequency shifting. So across the near infrared, this can work over ranges of hundreds of nanometers. As an example, what is shown here is the red shifting of the output of an erbium-based system in the near infrared. If even lower frequencies are required or longer wavelengths, one might combine the frequency shifted wave with the original wave in a process referred to as difference frequency generation. This allows to access the mid-IR range, the mid-IR spectral range, or even further beyond. Last not least, the common way to expect the spectral coverage is supercontinuum generation. So supercontinuum generation, simply speaking, converts pulsed laser light into coherent light with an extremely broad continuous optical spectrum. And as illustrated here, such a spectrum might span hundreds of nanometers or even 1,000 of nanometers in bandwidth. Yeah, and this can be also done, so to say, at different central wavelengths. So this was a brief overview or intuitive overview of some of the tools that we have available in our toolbox. By no means a complete one. Yeah, and hopefully this provides an intuitive picture of the many possibilities that we have. And yeah, with this toolbox in hand, let us now move from the technology side to some real-world application examples. So there are 4 fields which we wanted to spotlight today. What do they all have in common? I would say, well, in each case, the femtosecond pulse train will need to be tailored to some application-specific requirements. And yeah, this can be done by our box of tools. So to start, in ultrafast spectroscopy, laser pulses are employed to examine the dynamics of optical excitations typically on a femtosecond or picosecond timescale. One typical example, as you might know, are so-called pump probe experiments, where a pump beam is used to excite the sample, and a probe beam is used to monitor the pump-induced changes. And often a specific pump wavelength is combined with spectrally broad probe pulses. So here comes an example of a system configuration serving such an experiment. The design starts with delivering the erbium fundamental as a pump beam. Now employing our toolbox, we might split off part of the erbium fundamental for supercontinuum generation, for example, for a broadband probe in the near IR range. Should pump beams in the in the visible spectral range be also required, one might split off another part of the fundamental for second harmonic generation. And again, if you need again a probe pulse in the visible range, one can again split off a part for supercontinuum generation, this time spanning almost the entire visible spectral range. So without going into more details, but we can provide systems, so it's possible to design systems that will cover an overall wavelength range of almost 2,000 nanometers. Let me briefly highlight two benefits here. So first of all, our toolbox enables highly flexible multicolor laser configurations. And at the same time, we will be looking at really turnkey solutions that are compact and maintenance-free. So there is no tweaking, no user adjustment will be required here. Having looked at this example in a rather scientific context, let me turn to two industrial applications, starting with the rapidly growing field of 3D nanoprinting. So what is 3D nanoprinting? Quite generally speaking, I'll say 3D nanoprinting is the nanoscale variant of additive manufacturing. It relies on two-photon polymerization. Actually, it's conceptually quite similar to multi-photon approaches in microscopy. As illustrated on the left here, two-photon polymerization relies on pulsed laser light, initiating polymerization of a so-called photoresist. And the photochemistry will start only upon simultaneous absorption of two photons, with the probability of such event being non-linear in light intensity, unlike linear absorption. So in practical terms, for a laser beam focused into resist, significant two-photon absorption occurs only in a small focal spot, ensuring spatial confinement. And in fact, like in multi-photon microscopy, resolutions below the diffraction limits may be achieved. How does it look in practice? So this is a very basic scheme of a 3D nanoprinting setup, shown here on the left. Typically, a fast acoustic modulator is employed for power adjustments, and the beam focus is spatially scanned with galvo mirrors. In essence, this allows for 3D nanoprinting in small volume pixels, or so-called voxels, they are called in the community. How can we serve such a setup with our toolbox? Well, typically we will require frequency doubling of either the erbium or ytterbium fundamental into the visible spectral range to match the photo initiators for the two-photon polymerization process. Also, one will typically require to combine this with fast modulation and dispersion precompensation, so to ensure shortest possible pulses at the focal spot. 3D nanoprinting can be employed for a lot of applications, like printing biomedical structures in life science, the design of micro-optics, microfluidics, micromechanics, some micromechanical parts. The application that we wanted to briefly spotlight here is related to integrated photonics, namely photonic wire bonding. Simply speaking, photonic wire bonding, it can be considered as the optical analog to metal wire bonding in electronics. It relies on fixing discrete photonic chips onto a common carrier, embedding the interconnect regions into photoresist, and then 3D nanoprinting the connecting waveguides. So the technology, it not only shortens innovation cycles of photonic integrated circuits, but nowadays also aims to serve really high volume production lines. So what are the key ingredients that femtosecond fiber lasers deliver for such a setting? Well, they deliver the beam pointing stability and the beam quality that you need in a 24/7 operation mode. They come with easy to integrate and compact solutions, also for power modulation and dispersion compensation integrated. And last not least, they will lead with pulse-to-pulse repeatability and reliability. Before moving on, we wanted to show you yet another very useful implementation of 3D nanoprinting. So what you see here is the image of a 3D nanoprinted beer mug from one of our customers, very probably the smallest beer mug in the world. As you can imagine, with Menlo Systems being headquartered in Munich, we have some internal debate if this could be turned into some kind of attraction or maybe even business case at the forthcoming Oktoberfest. This is still going on. We'll need to see. Yeah, we'll need to see how we get there. In any case, for the next example, we are shifting to a completely different range of the electromagnetic spectrum, the range of terahertz radiation. So in a nutshell, terahertz radiation occupies the middle ground, so to say, between microwaves and infrared waves. Why is this region of interest? There are quite a couple of reasons. So terahertz radiation penetrates non-polar materials, so it's suitable to characterize materials like polymers, paper, wood, ceramics, you name it. Terahertz waves are highly sensitive to water content, so this makes them interesting for environmental or food monitoring or tissue analysis, for example. And last not least, terahertz spectroscopy can unambiguously identify molecules through distinctive absorption and dispersion features. Nowadays, how does terahertz time domain spectroscopy work? Well, commonly it's a combination of femtosecond lasers with so-called photoconductive antennas. What is the principle behind? So basically, in both terahertz emitters and in terahertz receivers, a femtosecond pulse is used to generate charge carriers in a photoconductive material. In a terahertz emitter, the charge carriers are accelerated by a bias voltage to generate the terahertz pulse. And so to say, the opposite happens in the terahertz receiver, where the terahertz pulse itself is used to accelerate the charge carriers and to generate a current transient that can be amplified and measured. Now let me show you how we can use our toolbox to assemble a terahertz time domain spectroscopy setup. It will be based on of course, on a femtosecond oscillator with a split or dual output. After amplification of each of these outputs, optical fibers can be used to deliver the laser pulses to the terahertz emitter and the terahertz receiver. And these can be arranged for either transmission or reflection measurements or both. Last not least, a delay line is employed in one of the arms for time domain scanning. Now, in some instances, so-called optical pump terahertz probe experiments, the terahertz transients shall be measured after optical excitation of the sample. This is actually no problem for our toolbox, as we can derive yet another arm for generation of the optical pulses. So shortly speaking, such schemes can be specifically tailored for both scientific and industrial settings. Let me highlight one example for each case. So the upper figure here is taken from a Nature paper in which the authors demonstrate optical generation and manipulation of currents at the nanoscale by employing optical pump terahertz probe experiments. This is considered as a crucial step towards scalable optoelectronic systems in microelectronics. The example below, this is an industrial grade terahertz system in action, used to determine the thickness and defects of car body paintings to improve the productivity of the painting process. Boiling it down, I would say, by increasing the process knowledge and the process control, one is looking at less than 2 years for return of investment of such a system. Now, what are the key ingredients that femtosecond fiber lasers deliver here? Well, they can conveniently supply the terahertz antennas via fiber delivery, actually of over up to 50 meter. They offer a modular oscillator amplifier concept that allows for cost-effective multi-bridge systems. This goes particularly well with terahertz applications. They allow for cost-effective extension into optical pump terahertz probe schemes. Last not least, they come with the robustness and reliability that will be required in industrial settings. Now, before closing, let us finally turn to an application field that has emerged for us, I have to say, relatively recently only, namely photonic quantum computing. So what is photonic quantum computing? In a nutshell, or at a very high level, photonic quantum computing uses photons as qubits rather than matter-based systems, such as trapped ions, neutral atoms, or superconducting circuits. This is certainly not a profound definition, just a pragmatic definition, but you might think of photonic quantum computing as of generating single photons and then manipulating and routing individual photons through optical components in a very broad sense, like waveguides or fiber networks, as illustrated on the left here. In a quite intuitive picture, you might compare it you might compare the photons to ping pong balls, which are passed through a forest of poles or obstacles before being collected in different bins, as shown on the right here. Again, these are certainly not profound definitions, but what I should emphasize here, that one of the key advantages the key advantages that are considered in photonic quantum computing is room temperature operation on the one hand, and on the other hand, the compatibility with existing telecom fiber infrastructure. And both of these points make it a very promising approach to scalable quantum computers. So a key resource in photonic quantum computing is the generation of entangled photons. I'm assuming most of you will know. So entanglement means that two particles or more particles remain correlated, so their states cannot be described independently. This is what Einstein called the spooky action at a distance. The most common method, a very common method for generating entangled photons is so-called spontaneous parametric down conversion, or SPDC, as illustrated here on the left. Simply speaking, in SPDC, a pump photon from a laser passes through a nonlinear crystal and is converted into two lower energy photons. And under the right conditions, let's say, simply speaking, these photons become entangled. So what are the requirements for the laser source now to be efficient in generating entangled photons in this way? It turns out that there are two main requirements for such a source. So first, its spectral bandwidth. It turns out that the spectral bandwidth should match the relatively narrow telecom wavelength grid. And this translates to pulse durations at the bandwidth limit into pulse durations around 1 picosecond. And second, to drive the nonlinear process, a high spectral power density is desirable. The scheme here on the left illustrates our toolbox approach towards realizing such a source. Essentially, I mean, there are a few tricks here, but one of the main tricks is that it relies on spectral filtering before amplification. enabling truly bandwidth limited pulses in the picosecond range. As you can see, we have not yet decided on the color we will give the box here. To conclude, before closing, I would like you, we wanted to show you some preliminary but real performance data from such a laser source designed specifically for SPDC. In short, the system enables turnkey generation of picosecond pulses at 780 nanometers, operating really close to the transform limit and delivering spectral power densities of up to approximately 1 watt per nanometer. I should also mention that we plan to offer an optional carrier envelope phase stabilization feature. So a comp variant or a comp optical comp version, if you wish, which can further improve the indistinguishability of consecutive photon pairs, which is required in some applications. So with this, let me wrap up. Fiber-based femtosecond lasers exploit state-of-the-art mode locking technology. They really facilitate modular and highly flexible design concept. And this is, to wrap up, why we consider them to be robust, reliable, and ready to use. Thank you for your attention, and Kristen and me are looking forward to questions and feedback.
Thank you so much, Jaroslav. This is really good technology because this is a way actually to bypass old absorbers. So there are several questions in the chat, in the Q&A, and coming into the messages. So we can start. I will start actually for the last one. So in the mid infrared, how strong a photocurve can you deliver, and in kilohertz repetition rate? Is it in kilohertz repetition rate?
So maybe I can jump in and
Yes.
Hello everyone. Yeah, I mean, if we talk about femtosecond fiber lasers in this compact design, and if we concentrate on the different frequency generation Jaro mentioned, it strongly depends on the nonlinear crystal and the damage threshold and the conversion efficiency you have there. With our solutions, we can provide, for example, in the 3 to 5 micron regime, which is quite important for fingerprint region of many molecules, 100, 200 milliwatt, for example. That's depending on the repetition rate, a few nanojoule. That's the maximum. For longer wavelengths, it strongly depends on the crystal you're using and the damage threshold there, or vice versa, the conversion efficiency. If kilohertz is possible, yes, definitely. I mean, we are providing seed sources for our end customers, but then we are talking more about scientific solutions, much bigger ones. And then, of course, with special designs, you can also get kilohertz and very high power level in the micrometer regime.
Excellent.
So we're happy also to share some results. It's also on our webpage. Some customers of us did really fancy things with our femtosecond laser as a starting point. But then this adds more and more amplifier stages and more complexity.
Mm-hmm. Yeah, that makes sense. That makes total sense. Thank you so much, and it's good. I mean, if there is any information that you want to be shared, please contact us or contact directly to Menlo Systems. You are going to receive. Somebody's asking if you are going to receive the slides. So this is this session is recorded and is available at the Optica webpage, and it's going to be available. You are going to receive all the information after this in an email. So I would like to continue. So stay with me, Wagner and Emmanuel, because I know you raised your hands. But let's go a little bit with some of the questions that we have in the Q&A box. So, how does internal structure of your Elmo different to the Elmo?
Yeah, first, so exactly. So that's actually names of our compact femtosecond fiber lasers based on erbium, so at 1550 nanometer roughly telecom wavelengths. and the other one is at ytterbium at 1040 roughly. The main difference between them is that with the telecom wavelengths, you have access to both dispersion signs in the fibers we are using. So you can stretch the pulses and you can compress them. And by this, you have a purely fiber-based stretcher and pulse compressor. And due to the fact that we want to have short pulses and also manage the dispersion intra-cavity, so in the fiber loop, which is generating the laser oscillator, we will manage or we have to manage the dispersion for low noise performance and shortest pulses. And there, erbium can be designed as a purely fiber-based solution, where the ytterbium systems, they have a small free space section. Therefore, the oscillators are typically a little bit bigger, where we have to match the dispersion. So with fibers, you would need to use photonic crystal fibers or some grating compressors or prism compressors to compress the pulses and manage the dispersion. That's the big difference.
Yeah.
Both are working, both are really reliable. Telecom wavelengths are more common. The ytterbium wavelengths are more for high power applications. There you can really boost the amplification. That's then the main difference.
Yeah, absolutely. So we have Kit Willis asking, is the toolbox you presented all fiber-based tools or are they free space tools? So that was an early question, to tell the truth.
Yes, actually, that's quite related to the question before. It strongly depends. I mean, some of the processes, they are more or less only available in free space. Therefore, free space compressors, which are not accessible due to the dispersion, or which is limited maybe by the pulse energy and the nonlinearities you create, or the damage threshold, and therefore you have to switch from fiber then to a free space part. So second harmonic generation, different frequency generation. Many of the spectral shifts we are showing, this happens in customized fibers, photonic crystal fibers, high nonlinear fibers. But still, the big advantage is that we really minimize the free space part. So it can be more compact and more robust. You have not to deal with huge cavities where you have to align things, where they're purely maintenance free, and you can produce them more compact and reliable, even with some small free space sections.
Yeah, so I'm going to start asking our speakers that raise their hands to talk. So Warner, we will start with you. Please unmute yourself. Tell us who you are, where are you coming from, and what is your question? Wagner?
Hi, do you hear me?
Yes.
All right, so my name is Wagner Buono. I'm originally from Brazil, and I'm starting a lab in South Africa on nonlinear optics at the University of the Witwatersrand. So all of the specifications that you've presented for your laser systems are amazing. I really like it. I worked with femtosecond lasers in the past that were non-fiber based, and the maintenance was a big problem. So the prospects of having a femtosecond laser with these specifications that work without maintenance, it's really good. But then, as every other researcher might have been wondering, can you give some kind of order of magnitude for a price for the system?
I mean, it really strongly depends what design or wavelengths you need. I mean, with the small box Jaro showed in the beginning, looks like the former video cassette. I mean, this starts at 10, 15, 20K, depending on the output power level. And then there's actually not really a limit. I mean, due to the modular concept, you add amplifier, second harmonic generation, maybe locking electronics to fix the frequency. And this is then, of course, adding complexity and costs. But so, for example, a 1 watt level 780, so the frequency doubled. We showed it's in the range of 60,000, 70,000, 50,000, depending on the exact configuration. And also important is for many of these femtosecond lasers, we are using really maintenance-free technology. So there is the pump diodes, they are telecordia specified. Also the multimode diodes, they have very long lifetimes. So typically we don't see an increase of the failure rate during the lifetime. So this is not limiting. So we can really truly recommend our customers that they can leave the system on forever, which is actually true for a lot of systems. And for our optical frequency comms, they are designed really for 24/7. So you don't have to deal with pump diode replacement, maintenance or service intervals, and so on.
Okay, thank you. So, and in any question, I mean, if you are really are interested in this laser, so please contact Menlo Systems or contact us, and we can make the introduction. So we have also Emmanuel. So Emmanuel Rodriguez, would you please tell us who you are, where are you coming from, and what's your question? Emmanuel? Seems like Emmanuel is not ready, then let's move to Mashesh Kumar. Mashesh Kumar, so now you are allowed to talk. Could you please tell us your question?
Yes, thank you very much, everyone. My name is Mahesh Kargar from India. I have also carbide femtosecond laser for cutting micro precision. It is a solid state. But in future, I'm looking for micro nano structuring works, like to making a nano bubble under the surface. So we are actually working in ultra hard material and monocrystal PCD transparent material. So is there any possibility to do in your lab, or if you had already sold your system to anyone, and we can do some nano work under surface of high transparent and high brittle material? So my question is, yeah, please go ahead. Sorry.
I think it depends a little bit on the exact requirements. So we are providing demo units for customers. If we have demo units available for testing, we can also share results from existing customers or publications, highlighting some of the limitations or advantages. That's definitely possible. So I think the easiest way would be that you directly contact us and we double check what's possible.
Thanks a lot for them. And actually, I used to travel quite a lot Germany. I traveled, I think, more than 30, 40 times in my life. And since 1989, 90, we are using laser machines for several applications. And right now, we have almost 400 plus laser in-house, included coherent star cut, included a certain laser automicrojet from Sinova. We have a 40 laser automicrojet and the IR nanosecond. And we are the biggest service provider in India. So since 1989, my first laser job started in 1989. I almost 36 years in laser. So now we wish to enter in a femtosecond application in India, because India is now upcoming market for world. So I wish to address certain application which is suitable to semiconductor or doing some pockets or wafer works or microstructuring work. I'll be very thankful, and if required, I'll be visit myself, and I'll definitely send an email to you today about my company. We are 550 plus people, and with the God bless, we are doing a lot of work for American customer, Japanese customer, and from Israel customers, from like a kind of micro machining services. So very
Thank you
happy
so
to
much,
have
Makash Omar. Yeah, thank you so much.
Yeah, please contact us and then we can discuss it in detail.
Absolutely. So yeah, let's continue with one of the questions that we have in the Q&A. So that is one that it says, why the spectrum does not show the Kelly sidebar?
The Kelly sidebands, the spectrum. the Kelly sidebands, when do you get Kelly sidebands? Typically, when you have a lot of dispersion, and you get a kind of soliton shape. Typically, the lowest noise performance we manage if the net cavity dispersion is around 0. With this, you get broader spectrum. You don't see Kelly sidebands. And that's, of course, requires some pulse stretching and compression, so to compensate the dispersion in the oscillator. And we get broader spectrum out of the oscillator, and which is helping for short pulse applications. And at the same time, it's reducing the noise performance. Therefore, you don't see Kelly sidebands.
Yeah. Now we are moving to the quantum application. So can we create entangled photon by applying a femtosecond pulse to our SPDC?
I would definitely say so. We are
Exactly.
we can provide some recent publications where some project partners did great work.
Or even, sorry to interrupt you, Christian. Thanks for answering all the questions. I was thinking, I mean, we might even connect with reference customers. So we'll be happy to take to look in detail into this offline. Yeah.
There are some recent publications from project partners and end customers.
Yeah, absolutely. So Emmanuel, raise the hands again. Emmanuel, are you ready to talk now?
I think so. And do you hear me?
Yes.
Yes.
My name is Emmanuel. I come from Mexico, from Ensenada, here close to the border with the US. And I'm a PhD student at a optics program here at a research center. And I'm developing a laser system based on erbium fibers. And what we have in the lab is a very narrow spectrum. And we think we may face something that related to what you were talking about, like we are not compensating dispersion properly. So we have a very narrow spectrum. We are seeing Kelly sidebands. And I would like to ask you about some advice for reducing these Kelly sidebands. Is achieving zero dispersion in cavity going to improve our spectral performance and also reduce our temporal performance?
So I mean, it's depending what you want to have in the end. So if you have some Kelly sidebands, of course, you can also get rid of them by spectrally filtering, because typically they're sitting not at the center. This is helping for later amplifications, but you could also manage the dispersion inside the cavity with free space components like prisms, gratings, or you address it with different fibers. So typically the active fibers, they have an opposite or a different dispersion regime than the standard PM fibers, if we talk about the erbium wavelengths. And then you can use a lot of nonlinear steps afterwards to broaden the spectrum and to get shorter pulses. So
Thank
playing
you.
with cell
Another
phase
question
modulation
if,
in fiber or some high nonlinear fibers. So there are different approaches depending on what's the
Another
final
question,
goal.
if we still have time, what's the average power your systems are capable to deliver? I mean, the erbium laser systems you have available.
For erbium, our model was the highest average power is roughly 3 watt, more than 3 watt, 3.5 watt at 100 megahertz. So this translates then in a more or less high pulse energy in the range of tens of nanojoule.
Yeah. So we also have Juan Arango Juan Arango, could you please tell us your question? Juan?
Yes. Hi.
Yes.
Hello, I am currently based in Jena, in Germany, and for a new setup we are planning on building for nonlinear characterization of materials. I was wondering if your technologies, maybe with additional modules, would allow for either spectrally tuning the central wavelength of your pulses in the near infrared, and or if it's possible to tune the precompensation of the dispersion so that you can, by changing samples or setup configurations, decide where the pulse is getting compressed over the optical path.
So in the near infrared, it's depending a little bit on what wavelength range you're interested in, the exact wavelength range, and also the power levels. So tuning the output spectrum is possible. This you can do for some of our systems just by the pump current. So everything is fiber coupled. You can shift the spectrum, like Jaro showed, in the range of 1800 nanometers, 1600. We can also provide a broad spectrum, or you can generate a broad spectrum with one of our lasers using some additional nonlinear optics or photonic crystal fibers. And to tune the dispersion, if you have a fully fiber-based solution, that's also possible, but then you need some extra kind of tuning knob where you can adjust the dispersion. Or if we have some kind of free space compressors already integrated in our systems, then it's easily done motorized or just by a hex key where you can align it and optimize it for your experiment or the maximum spectral width. Or
Yeah, it's possible to do it. So, Emmanuel, I will recommend you to keep in touch with Roland and Christian. I mean, totally. So something. I mean, we are actually running out of time, but there are the classic questions that we have to do. This is because we are talking. This is going to be. This is for Richard, yes, but this is actually for being deployed in the industry. So, what is the typical lifetime of such a fiber lasers?
There's actually not a really easy answer or a quite easy answer, depending on the point of view. So the nice thing is that due to the fiber concept, it's in principle maintenance free. So typically you don't have to deal with alignment or stuff like this. So there's also not a specific service interval or service visit required. The telecordia diodes, the telecordia pump diodes will also allow that typically in the lifetime of your laser system, there are no issues by replacing pump diodes or degradation. And also the nice part of the figure 9, to come back to the technology, is that it's a purely interferometric approach based on telecom components. So there is no degradation like for a satellite absorber, no change on output parameters. That's fiber telecom components which last more or less forever.
Yeah, there is another question that came here it came to me. So is that is it so in the figure 9 technology, why is the NALM operated in reflected mode than in transmission?
Typically, we try to operate it like Jaro showed in the reflection mode.
Yeah.
This allows that you have a kind of sigma arm, and with this arm, maybe I can show it in a second to have it easier. So in this one, in this part, it's easier to integrate also to have a higher output power and also to integrate some actuators.
Yeah. Yeah, makes sense.
Also to adjust the cavity length here to keep the overall length stable. This means that the repetition rate is stabilized, and you can also integrate actuators which are acting on the dispersion to stabilize the carrier envelope offset frequency for our frequency comps.
Yeah, absolutely. Yeah, and you can keep it stable very fast. So thank you so much. So let's wrap up a little bit. So there are if you have more questions, please don't hesitate and contact us. Contact Menlo. So we are very happy for this. Many thank you for this technology. I mean, it's really just, as I say, it's just a bypass towards conventional saturable absorbers. It's really nice. I found the 40 nanoliters bill is adorable, but the thing is, it's not only that. I mean, it represents Germany and the Oktoberfest culture, but this is something that it can be used also in bioanalysis. So this is the kind of things that actually can see translate. So something that we can see adorable, it could be actually very useful in real life. So I will thank you, Christian. I will thank you, Jaroslav. I thank you, Menlo System, for all the support, for such a great masterclass, because they have been a masterclass, to tell the truth. And I thank you all for everything. So please be in contact. Thank you so much. This is Elena Diaz, Optica. Bye.
Bye-bye.
Thank you. Bye.